Hello, welcome back to Cracking the Cryptic, and a fascinating looking puzzle today. Now, I have switched off one of the lights in my room because I'm fed up with my head having a shiny bright light on it since we got a bulb fixed. Tell me if it's too dark now and I will go back to that. Probably just some bizarre sudden sprouting of vanity. Now, there are also noises, which incredibly is not the flat behind me. It's a Saturday. They're not at work anymore. There's a carpet being relaid in our group block of flats here. I mean, honestly, did all this noise happen before I started making videos? Maybe I just never noticed it then, but I was told they would be finished today and I thought it would be by now, but maybe it's still going on. Anyway, you may hear a little bit of hammering. Hopefully it won't be too loud in this room. We shall see. It is loud elsewhere in the flat. And this puzzle is called Remnants. Now, I think that is a real English word, and I don't know what it means. There's not many words you can do that to me with. I suppose it means remaining, something remaining or remaining, I would assume from the Latin. And Emfirio, I don't know what that means. There was Porphyria is a character in the Basil Pot by Keats, I think, and if not, in a similar poem. And that's the only place I know Phyri from, and I don't know what it means. It's obviously from the Greek. I don't know what Emfirio means. I think Emfirio is featured on the channel before. A puzzle by Simon, perhaps. Anyway, look, for some reason we are delving into the edges of my memory here, and there's no point doing that. What I do remember is that we still have 9 days to go on the Patreon reward, the Paint by Numbers Institute puzzle packs that are fantastic, and you can see those on Patreon. Do join us if you haven't already. We welcome everybody there, as does everybody at Discord if you join that. And the other things you can do associated with the channel are buy our apps. We are working very hard on a domino app, which will be out soon in some form, and yeah, we're looking forward to that. But there are lots of other apps available, including an arrow app, which is very appropriate as regards this puzzle, because this is an arrow Sudoku. So normal Sudoku rules apply, and digits along an arrow sum to the number in the attached circle. But what you'll note in this puzzle is there's a absolute heap of arrows, a full quiver of arrows, and many more, and that they're all 2 cells long as far as I can see so far. It looks like it. It looks a very clever design. Fascinating that this is unique in terms of a solution, but I'm certainly going to trust Emfirio, and I'm very prepared to give it a go. So do try it on the link under the video if you fancy it. I'm going to try and start now. Let's get cracking. Oh, I see. Yeah, okay. We've been here before. What was the puzzle that had these? Okay, we had a puzzle before that I called an eternal triangle. There was a diagonal constraint along this axis, and it had these 3, and they all had 3 sets of 2 arrows sprouting out, just as this one does. I mean, I know this has 4 arrows coming out of it, but it only has 2 in box 9. So I think these 3 are more important. They have to be 7, 8, or 9. And how do I know that? Because they're the only Sudoku digits that can have 3 or more ways of making up 2-digit sums. And these ones all do. But, well, I'm wondering whether they all have to be different, but I don't think I'm likely to be able to prove that without this diagonal being available. So these 2 could easily be the same. They quite likely are. Okay, so I don't really know what them being from 7, 8, or 9 means. I do know that it means the blank spaces in these boxes, which don't have arrows from them in the case of the 7, if there is a 7 in one of these circles, these will be filled with 8, 9. In the case of the 8, if there is an 8, these will be filled with 4, 9. And in the case of 9, they'll be filled with a pair that add up to 9. But that last bit has so much license, it kind of torpedoes the usefulness of the rest of the thinking there. This, I suppose, could be 5 or 6, as well as 7, 8, or 9. It's hardly worth pencil marking. I don't really know how we're meant to get some idea of what to do. I think there's only so much we can do with boxes 1, 3 and 7. They look useful, but not yet. So maybe it's these arrows going into boxes 2, 4, 6 and 8. What are they setting up? Because they seem quite interestingly positioned to me. I can see that whatever is the higher number of these two, which have to be different, the higher number can't go on these arrows because it couldn't go on its own arrow, and it couldn't go on the lower number's arrow. So it would have to go in this domino. Same applies down here, of course. I mean, actually, the same applies here. Again, the higher number will have to, it couldn't go on its own arrow or a lower digits arrow. So it would have to go in the other domino. Sort of row 5 or column 5 domino, but I don't know what use that is, if any. Ugh, crumbs, I don't know. What are we doing? What can we do? Oh, what's the total of all? Okay. Yes, I mean, I'm aware that I know that this pair is either an 8-9 pair or a 4-9 pair. Okay, so in one case, this, if one of these is a 9, it won't have a 9 in it specifically, but one of them won't be a 9. And in that case, at least, the other one of these pairs will have a 9 in it. So there must be a 9 in one of those 4 cells. Now, it would be quite an interesting leap to say that there couldn't be 2 9s in those 2 cells. And in fact, the only way there could be 2 9s is if there was one there and one in one of those. And in that case, this would have to become an 8-7 pair, because they couldn't be 9s anymore. And then 9 would have to be in one of these cells, and 8 would have to be in one of these two. And whichever one of these was a 7 would also have an 8 in the top rows. It doesn't quite get enough done, does it? Oh, hang on though, hang on. What about the total in box 2? Yes. Oh, yes, look at this, the total of row 3, which, not that it matters, but you know what the total of row 3 is because you know the secret. It's 45. Yes. That's quite interesting, because the total of box 2 is also 45. This is just a little bit of weird set theory. And I doubt that it's necessary, but it helps to see this, I think. So, in fact, this is a set of the digits 1 to 9, and this is a set of the digits 1 to 9. That's the important thing. So if we take out these 3 cells, we're still left with the same 6 cells in red as we have in green, and therefore the same totals. But if we take out this cell and those two, we're still left with the same totals. Not the same cells, because we only got 4 red and 5 green, but the same totals. And if we take out this cell and its equivalent in this circle, we're still left with the same totals. And the total of these 2 cells is the total of these 2, therefore, because the total of that green cell is the same as this. We can now convert, if you like, these 2 green cells into those two green cells. And the total of those two is the same as the total of these two reds. And we worked out that the higher number is in the reds, so it's the same two digits. Isn't that weird? I didn't see that coming at all. I did not see that coming. I don't see why that is. Is that obvious from the very beginning? When you look at those two, can you see they're those two? I don't know. But I do know we can work the same trick down here and with this box. If we do exactly the same thing, those two add up to those two. So those four are the total of those two, the same totals. And that means those two have the same total as those two. So, and are the same digits in the same way as here. That's so strange. No, how do we... Am I going to have to differentiate how this works? I don't know. These two are the same as these two. These... Oh, is it going to work with this? No. Presumably... I'm wondering if this has a different character, this... Oh, well, this is a four-legged pet, perhaps, a dog or a cat. These are weird five-legged mutant aliens, clearly. No, let's... In this row, does it work here too? Yes, I think it does. Those two have the same totals as those. So once you take those three out of the common... Okay, I'm just going to actually do it down here so that I can convince myself. Purple and orange... Delete the common cores, delete those that are equal to each other, make the purples into the circles. Yes. Well, it's the same total. Yes, the same, the higher lower digit thing still works. The higher digit here can't be on its own arrow or on the lower digit's arrow, so it must be there. So again, these are the same. Right. Okay, I've decided. I'm going to make these orange down here. Those two orange cells are the same as those two orange cells. Right, on the left, these two green cells are the same as these two cells. So let's make them both green. And now this is green stroke orange. Up here, let's get rid of the green from that. Let's make them both red. And those two red cells are the same as those two red cells. And over here, obviously blue next. Those two blue cells, it must work exactly the same here because this arrow pattern is the same. These two cells are the same as these two. And that is absolutely freaky. I might be on the track now. Yes. This is both in orange and green. And because it's in orange, it can't be in red. And this is red as well as blue. But it can't be the same digit because they see each other in column 5. So now I have proved that these three are different from each other. And this has to be different as well because blue can't be the same as green because of row 5. Blue can't be the same as... Sorry, this is blue and orange, this one. And it can't... Yes, so it's in orange and can't be red. It's in blue and can't be green. This one is red and blue and can't be orange or green. They're all different. This is green and red, so it can't be blue and orange because it's in those sets. And this one is... what is it? Green and orange. So it's in those pairs and can't be blue and red. That is so freaky. They're all different. And these are definitely formed from 7, 8, 9 pairs. They're all different. So this is not 7, 8 or 9, this bottom corner. Now this becomes the cell we should focus on. This is a 6 or a 5. And it appears in one of these cells along with a 7, 8 or 9. And in one of these. Which helps, well, which we could have sort of worked out by considering that that couldn't be a quadruple 7, 8, 9. Oh, come on, what is going on? So, this is 5 or 6. 5 or 6 only has 2 ways of being made up. Yes, this can't be 5 or 6. Now, how do I come to that rather staggering conclusion? Okay, let's assume that 5 or 6, whatever this is made up of a yellow pair. Let's say it's 6, and it's a yellow pair of 2, 4 there, and a grey pair of, oh, grey's useless, a light grey pair of 5, 1 there. So 2, 4 there and 5, 1 there. Could be the other way around. It must, in fact, oh no, hang on, they could be the same. Oh, bother, fish hooks. Okay, I was going to say that that pair can't be the same pair of digits as that pair. So if that pair, oh, okay, they would be the same. So that pair would be the yellow pair. Say that's 2, 4. This would be the grey pair, because that couldn't be 2 or 4. That would have to be the 5, 1 pair. Now this has to be the yellow pair again. This has to be the grey pair because it's in the same box as the yellow pair. Ah, this has to be the grey pair, and that would clash with this. So it doesn't work. My goodness, that took a lot of seeing. And I thought I was reaching that conclusion, but a different way earlier on. So the whole point of that is to say that this is not the 5 or 6. This is that 7, 8 or 9. This is the orange and green 7, 8 or 9. This is 5 or 6, orange and blue. How do we know about this? This is a different arrow. We know, okay, so if that's the 5 or 6, this would be yellow, this would be grey, this would be yellow, this would be grey. I don't have a way that that's broken. This could be either. I mean, I think there'd be a uniqueness issue if it was yellow, but I don't even know if that's true in this puzzle. No, that could get... Oh, no, there would be. But anyway, we're not using uniqueness. We don't do that because it doesn't prove the puzzle has a unique solution. And that's part of what we're trying to prove. So... Okay, so let's get rid of that colouring. That's not doing anything, and I did not establish whether this was 5 or 6 or 7, 8 or 9. It's lucky I got this one. Okay, this digit is there and must be in one of these 3 cells. Not very helpful. This digit can't be there, but it could be there or in one of these 2. Oh no, it is in one of these 2. That's what we've established earlier. Try and keep sight of this mark. I don't think it's 6. Sorry. No, that's not what I meant. The 6 was in my brain because of the calculation I've done. And that means I don't think this is the same as that. Because even at its maximum of 6, that pair adds up to 6. That's a 6. That pair adds up to 6. That's 3 lots of 6 is 18. Even at this one's maximum of 9, 9 there and 9 up there in that domino makes 18. Plus the 18 we have down here is 36. We'd need yet another 9, which would clash with that 9 to complete the 45 total for the column, which is the numbers 1 to 9 add up to. So even at 6, well, this can't... Okay, it doesn't tell me whether this is a 5 or a 6, but it does tell me this isn't the same digit, so it's not the 5 or 6. So the 5 or 6 this time is sitting... Oh, same as there, actually, is sitting here. That is the blue, orange 5, 6. It's now appeared in 3 different places in the grid. This is the same as that, so I'm going to make it the blue, red 7, 8, 9. Now, can we... I don't suppose we can determine these. The fact is 7, 8 and 9 have 3 ways of making up 2 cells, so there's just a lot less pressure on how it's getting done. But maybe the total down here is still helpful. If this was 5, this would only add up to 10. If these were both 9... Ooh, touch and go. Yes, it would just work. If that was a 5, you could have 5 here, 9 here, 9 here, 9 here, and 8 here. And I suppose you could reverse that around and have... No, you couldn't have a single 9 here, because that would clash with that. Yeah, so 5 there is 10, because you double it, because it's once in the circle and once on the arrow. Double 9 up here is 18, that's 28. This set, at a minimum, therefore, if this is 5, adds up to 17. And the only way you can do that is by having an 8 here. It can't be a 9 because there's a 9 in there, and a pair that adds to 9 here. So that can be done. So I didn't quite prove that this couldn't be 5, but it's very difficult for it to be 5. If it's 6, there's a degree of freedom. Maybe that's still going to stop this being 7. 6 doubled is 12. If this was... Oh, yeah. If this was 7 doubled, it's the same digit as here. So it would actually be 7 tripled is 21, and that would be a 12 to make up the 45 total. So this is not a 7. If that was a 6, I don't think it's going to work with an 8. You'd have 24 and 12 is 36. Oh, it does, and that would be a 9 then. Oh, okay, so that does work. That's interesting, though. So is this a 5 or a 6? That's probably not the question at the moment. We've got a 7, 8, 9 triple in the middle row. We've got 7, 8, 9 triple down here. Okay, this finally does prove to me that this... No, I think I established earlier, these have to be a 7, 8, 9 triple. But anyway, this is another proof of it. Those 2 red cells are those 2 cells. That green and orange cell is that cell. So those 3 have to be different because they're different in the central column. And they're different in this column. Oh, I don't think it tells me which of these is which, but 7, 8, 9 there. Now, that means that in one of these pairs across here or down here, there is a 7 because they're all different. No, in both of them there's a 7, but in one of them, I was going to say in one of them 7's on the circle, but I don't think I know that. 30, 24, 30. Oh, this is getting too big now. Oh, this is so strange. Hang on. That adds up to 24 in the central column already, the 9, 8, 7. If this is a 6, that's 30. Then if you keep these to their minimum as a 7 and 8 arrow, that's already 45. This can't be a 6. This is a 5. And in fact, yes, these are 7, 8, 9, but the arrows pointing inwards have to be a 7 and an 8, I think. 9, 8, 7 is 24, plus the 5 is 29. You can make that pair add up to 15, and that's a 1. That's the only way you can do it. This is a 7, 8 arrow, pair of arrows. This red is 9. I don't know which one of these it is, but this isn't 9 now. This is 7 or 8. And now going across here, it's different because that's not on this arrow. And that may be the only way we get to tell. I don't know. Right, 9 is not in that pair now because it's up here. That pair, therefore, is not 9, 4, and this is not 8. That is 9. So that red-blue cell is this one up here. This is the red-green that is the same as that. With a 9 up there, this pair is... I don't know, but it adds up to 9. But I do know that this pair has a 9 in it, so I can place that. This is now not 9. This is 9 because it's the same as that cell, so that's another way of proving it's not 9. And I still don't know how to divide red, green and orange, green up between 7 and 8. I do know that the total in this column works. What about the total here? I don't think it's going to be any use. 24, 29, 30. then this pair adds up to 7 or 8. And this pair adds up to the other of 7 or 8, but that could be anyway. Look at the arrows in this column. We're going to work out what this is now. I don't know what it is yet, but that's one set of 9. That's another set of 9. That's a third. That's 3 9s is 27. 5 and 5 is another 10. That's 37, and this is an 8. Then these two 9 arrows are not 8 1 or 5 4. So they're 2 7 and 3 6 in some order. And we're left with 1 and 4 on the 5 arrow, which is perfectly acceptable. Actually, again, by uniqueness, I could decide this isn't a 1 4 arrow. I'm not using that. Now, if this is a 7 arrow, it's a 2 5 pair. That's not what to do. Oh, there's a 5 somewhere up here. Yeah, that's quite interesting. This is effectively another 9 arrow, just like that and that, because once you've eliminated 3 sets of 9 in the box, that's a 4th set. So wherever 5 is up here somewhere, 4 is outside it here, either on this hypothetical arrow or on those two genuine arrows. And that means 4's in one of those cells, and this is a 1, which is quite strange. And that does mean that 4 is not on this arrow at all. Or put another way, that this can't be a 4 and a 1. So this is a 2 3 arrow. This is a 4 1 arrow. I know this is going to be a 2 3 arrow, but I can't prove it yet. Or can I? Yes, I can in this way. 2 and 3 are now a pair there and can't be there. Sure, one of them could be on this arrow, but they can't both be on this arrow, because this would add up to 5 then. So at least one of them's on this arrow, and once one of them's on this arrow adding up to 5, the other one is as well. So that's a 2 3 pair. This is either 1 8 or 5 4 on this arrow at the top. I have a feeling I should probably know which it is now, and I don't. I mean, I suspect it's 5 4, but I don't know that. This one also can't be 4 5 or 1 8. That is 2 7 or 3 6. The 1 is in one of these 3 cells, so the 8 is over this side. I thought that was about to run dry there, and it did. Oh, this is such a clever puzzle. It's absolutely mad. Right, if this is 8, this can't be 5 3 or 2 6. If this is 8, this is a 1 7 pair. If it's 7, it can't be 5 2 or 3 4. It's 1 6. So it's either 1 6 or 1 7, and definitely has a 1 in it. So this is either 1 6 7 or 1 7 8, and definitely has a 7 in it. So these are from 4 6 8 and 9. Now this cell can't be 8 or 9 on this arrow. If it is 6, that's an 8 and this is a 2. If it's 4, that's a 7 and this is a 3, which is a weird collocation as well. So in fact, on one of these arrows there is a 6 2 pair, and on the other there's a 4 3 pair. Now 4 6 4 is definitely there. 2 3 and 5 are definitely here. What can this be? If it's an 8 arrow, it's 1. Oh, it's got a 1 on it, hasn't it? So it's the same as this. It's either 1 6 or 1 7 with a definite 1 on it. Now I want to say there's definite 1 on that, which would be great, but there could be a 1 there, so I daren't quite say that yet. Now this can't be the 1 arrow version of this, and it also doesn't have a 4. So if this is a 7, that's a 2 5 pair. If it's an 8 though, I suppose it could be 2 6 or 3 5. Now either way round, that's going to form a virtual 2 3 pair with that, because this must have a 2 or a 3 in it. The other one's there. This can't be 2 or 3. So this must be 2 or 3. And that doesn't help with this total that adds up to either... Well, no, this total of 4 cells definitely adds up to 15. So these two either add up to 8 or 7. And this can't be a 5. So it must be a 4 or a 6. And whichever one it is chooses what that is. Oh, come on, are we not there yet? If this was 4, 5, that would be a 6. No, I can't do that yet. I'd no doubt I'm missing something big at this point, but I'm getting there and I'm happy enough with that. It's such an interesting puzzle. I can't believe I haven't quite unwound all these 7s and 8s. I think, I don't know, I feel like I should have. Anyway, I haven't. Now, if that, oh, there's got to be a 9 in this pair because this is 7 or 8, yes. And that 9 is here, and that places a 9 here. Have I not finished doing 9s? No, nothing like. There's a 9 in one of those two, and somewhere on an edge, on a corner of the middle. Now, if that's an 8, this is a 4, but if it's a 7, this is an 8. So that is 4 or 8. Same is true up here. That is 4 or 8, depending on what that is. So we get a 4, 8 pair in the column. Now this is 7. This is 8, but I don't know which one of these it is. But it means these two add up to 8. 8, 24, 38. So these two add up to 7, so they are 4, 3. Wow, and we're there now, I think. 4 there, 3 there, 6 there. This is now a 2, 6 pair. Maybe we're not there with this 7, 8 disambiguation, but we got that 6 now. This can't be 6, 2 or 1, 7. So if it's 8, this is 3, 5. If it's 4, it's 2, 5. So it's definitely got a 5. And now I've got a 2, 3, 5 triple in the row, and this is a naked single. This is a 9. Sees the 2, 3, 5 triple in the row as well as 1, 4, 6. It sees 7, 8 in the box. So that's a 9 and that's not. And we're left with a little 9 X-wing in 4 cells in columns 4 and 6. Now this is a 7, 8 pair. That feels like it ought to be helpful. 5 is in one of these 3 cells. This is not 5, 2. Oh, it's not. Okay, if that's an 8, this isn't 2, 6 because of that cell, or 5, 3, or 1, 7. Yes, this has finally decided it. If that was an 8, this couldn't be 1, 7 because of that. It couldn't be 2, 6 because of that, and it couldn't be 3, 5 because of those. So that's the 7. That one goes up here because of the colouring. Therefore, oh, actually, ever since I got... No, I didn't know that was green and orange. No, that's the only thing that's decided that this is 8. 8 there, so that gets a 6, 2. We've got 3 and 4 on that arrow. The 6, 2 are ordered now. This is a 5, 9 pair for definite. This is not involving a 6, so that's a 2, 7 pair. 1, 6 there and a 4 on the other cell. This now can't be 4, 3 or 2, 5. It's 1, 6. This can't be 4, 3 either, so that's 2, 5. This is 4, 3, and that's an 8, and that's a 4 down here. That fixes 1, 4. That places the 1 here. This is now a 7 on the 8 arrow. There's no 2 there. 4, 1, 7. This is a 3, 5 pair, which we can order. This is a 1, 7 pair. This is a 2, 6 pair. Oh, the 1, 7 pair can be arranged. So that does 1, 6. That does 2, 6. That does 2, 5. That does 3, 5. These can't be 6 or 8. They are a 4, 9 pair. 3 and 2 are fixed there. That's a 7. 6, 8 pair down here. 2, 7 are resolved. 2, 3 are resolved. We're into beast mode to some extent here. This is a 2, 7 pair. We've got... Okay, let's look along the row. 5, 2, 7, 4, 9. This is either 3, 6 or 1, 8. Oh, okay, we're not in beast mode. This pair can't be 6, 1. Oh, that's 8, 7 has been resolved. I hadn't seen that. This can't be 4, 5. So that's 1, 8. This is now 2, 5. This is a 3, 6 pair. This is a 1, 8 pair that can go in. Okay, we'll get to the top in a moment. How am I going to do these? Oh, using that 7. Okay, or that 8 at the other end, yes. So now we've got a 1 there. We can do 1, 6. Now this can't be 6, 3, so it goes in here. 6, 3, 4, 3, 2, 5. We've got a 5, 4 pair at the top. At the bottom, we've got the 6, 8 pair resolved. Just 3 pairs left to go in some of the central columns, and we are done. There we go. What a brilliant puzzle. Remnants by Amphirio. Is it? I suppose it's all about the remainders, maybe, of these central columns, or kind of the second stage of the break-in is. I mean, that is a brilliant, brilliant construction. When you looked at that puzzle at the start and just figured out how it just looks like an explosion of similar things, and yet it's all disambiguated brilliantly. So clever. I hope you had a go at that. That is a wonderful puzzle. I'm delighted to have done that on the channel today. And I hope to see you again tomorrow. I think I'm seeing Simon about when you're watching this first. If you get to it early on, we're meeting up because of his birthday this week and my anniversary today. So there we go. We'll hope to see you again soon on the channel tomorrow. Maybe some gas tomorrow, because that was a struggle, but a good fun one. And I'll see you then. As it is, bye for now.